today my topic will be registers and counters. I need to finish this topic on Sunday. Maybe next Tuesday I will finish all the topics. We'll see. Right, so this is the outline of this presentation. Okay, I'll talk about registers first, and then I'll talk about shift registers and their applications. And then I need to talk about counters. We're going to see two types of counters, ripple counters and synchronous counters. So let us start with registers. So what is a register? Okay, it's a sequential circuit which is capable of storing data. If you have an n-bit register, you can implement it using n flip-flops, and you can store n bits. So notice that here in the register, we are connecting all of these flip-flops to the same clock. So notice that the clock here is connected to the clock input of all the flip-flops. It's connected here, 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 and here, okay? And also they use the same reset. And if I would like to reset this register, then I'm going to reset all the flip-flops and make them zeros at the same time. So here's an example of a 4-bit register, okay? Notice that how we draw the symbol, and this is the clock input, and this is my reset, okay? Now this register, so today, for example, if you have a CPU inside your computer system, there are many registers. Okay, there are many registers inside the CPU, and programmers use them actually to store the intermediate results of computation. So they store them inside registers. Okay, so this is the meaning of a register. However, the problem with this register is that every cycle we are changing the Q output. So the Q output becomes the D input at the rising edge of the clock. So cycle by cycle, we are changing the output to Q. Now, sometimes I don't really want to change the output to Q. So what I need is I need to control, okay, whether to load the data into a register or not to load. So we call it load or we call it enable, the same meaning. So this way we can control, okay, whether the register is going to change its value. We are going to load a new input data into the register, or nothing is loaded. So the question is, how do I change this design, which is shown here in this slide, so that we have a load input, okay, that we can use it to control the loading of the data inside the register? Any idea? How can we have a parallel load input, okay, to control the loading of the data inside the register? This is the question. So how to control the loading of data into a register? Of course, we can add a control input, a load input signal, but how do we implement the register? In other words, if I'm not loading, the register will not really change its value. So I'm not going to change its value cycle by cycle. I would like to control when to load and when not to load. Any idea?
We can put
yes, تفضل.
Inverter in front of the clock, maybe.
No, not an inverter. We need actually something else inside this register. And the way to do this, if I don't really want to change the Q output, what shall I do? Yeah, let us take a look here. So here we have the Q output, Q3, Q2, Q1, Q0. Okay, so these are the outputs, okay, of these flip-flops, and this is the output of the register. If I don't really want to change a Q, what shall I do? If I don't really want to load, I would like to keep the value of a Q unchanged. Notice that at the rising edge of the clock, so this is the rising edge of the clock, the value of a Q is going to become D. So if the input D changes, the output Q also changes. Now, what I really would like to do now is that I would like to control whether to change the output Q or not. So how to disable, okay, not to enable, yani I would like to disable the change in the output Q.
Use multiplexers.
Exactly, using multiplexers. And then what? Your answer is correct. So when you use multiplexer, what do? How do you use these multiplexers?
There will be a load control that will control the output of the which input will be used, whether it is the 1 or the 0, and we connect the last multiplexer with like if we used in maybe the adders.
Well,
So
here we
that
are, yeah, but this is simple. Yani, all what I have to do is that if I connect the Q output back to the D input, okay, does it change the output to Q? Let me repeat the question. If I connect the Q output back to the D input, does it change the output to Q? The answer is no.
No, it doesn't.
Yeah. So that's really the idea. So this is basically so what we are going to do is that this is basically the n-bit register, how we look at it actually from the outside. So now we have added this load or enable input. We still have the clock. This clock is connected, okay, to the clock input of all the flip-flops. We have n-bit register, so therefore we have n is the number of flip-flops that we are using inside this register. Notice that the input here is called I and -1 down to 0, and the output is called a Q. Now, in order to implement this register from the inside, what we need to do is that we need to add a multiplexer, okay, as shown here in this slide. So this multiplexer here, notice that how we are connecting the Q output back to the D input. So this is here Q3, this is Q2, this is Q1, and this is Q0. Now, if load is equal to 1, so load can be 1 or 0, right? If load is equal to 1, we are going to select here input 1. So therefore, we are going to select I3, I2, I1, I0. And we are loading this input inside the D flip-flops. And therefore, at the rising edge of the clock, we are going to change the output Q to become I. On the other hand, if load equal to 0, that's actually 0 here, then basically the D input is nothing but the Q output. We are selecting the Q output and we are feeding it back to the D input. And therefore, this will not really change the output to Q. So this is the trick here, is to use a multiplexer and to feed the Q output back to the D input. Now, if you use a multiplexer, yes, Osama.
So, Doctor, if the load is 0, like we are doing nothing, right?
Exactly. What we are saying is that don't load anything. So during this cycle, we don't really want to load. Next cycle, I would like to load. I would like to control whether to load or not to load. This is very important in sequential circuits. Sometimes you don't really want to change the output of a register, and sometimes you would like to change it. So this load here can control whether I would like to load or not, okay, whether to change the output to Q or not, okay? So if you use here load equal to 0, then you are feeding back the Q output back to the D input, and this will not really change anything. We are keeping the value Q unchanged, okay, in the next cycle. That's really the trick. Okay. Now these multiplexers, so these multiplexers, we can describe them with equations. Okay. So here DI, okay, so you can, for example, look at any D. Okay, for example, this one. If load is equal to 1, you get I sub I. So that's if load equal to 1. If load equal to 0, you have load bar here, you get a QI. So basically, this is the output. This is the equation for the output of the multiplexer. You can write it like this. Knowing actually how you write the equation for a multiplexer, that will be very easy. So if load is equal to 1, then DI becomes the external input, I sub I. And if load is equal to 0, then don't load anything, then DI becomes a QI. So basically, we are not going to change anything. So basically, you are feeding the output back to the input, and this will change nothing. So As I said, these registers are used a lot. They have actually many applications. When we would like to design CPUs, people actually use registers, okay, a lot, okay, in design. Right. Let me talk about the shift register. So what we have seen in the previous slide was a normal register, but we can design a register that will shift the bits. You can shift them either to the right or you can shift them to the left. Both are possible. So what is shown here in this slide, I have a right shift register that's going to shift the bits to the right. Okay. So notice that there is a serial input, which is called SI, that appears, that is connected here to D3. That will be the most significant bit. And Q0 is nothing but the serial output. So what we get here at the output, okay, that's Q0, is my serial output. And cycle by cycle, we are shifting all the bits inside this shift register. So they can be shifted in one direction or the other. But the point is we are shifting all the bits simultaneously. Okay, so because we are connecting the clock, okay, to all of these flip-flops, you can see that we are connecting the clock to all of them. So the shifting will be done in parallel at the same time. So that's actually very important to understand, okay, when you are designing a shift register, that all the bits are being shifted at the same time. Now, let us take a look at the timing of a shift register. So here I have, let us say, only a 4-bit shift register. Notice that here my input, my serial input here is SI, which is connected to D3. And my output here, which is a Q0, is my serial output. So I'm showing it cycle by cycle. Notice that the clock is connected to the clock input of all of these flip-flops. So all of them will change value at the same time. Now here I'm showing the serial input, which is connected to D3. And this is the value of the input cycle by cycle. So we start here at T0. So notice that this is actually the rising edge of the clock. This is the rising edge of the next clock. So when you think about these cycles, think about the rising edge of the clock, okay? Because all of these changes will happen at the rising edge of the clock. So all of these flip-flops are synchronized. So notice that how we are shifting the bits. So SI here, which is 1, is going, next cycle is going to appear at the output of Q3. If you have 1 here, then next cycle is going to appear here. Now, if this is 1, then it's going to appear at Q2. So if this is 1, then it's going to be shifted here. Now, all of this shifting is happening in parallel. If this Q2 equal to 0, then it's going to be shifted here. And if this Q1 is equal to 1, then it's going to be shifted out. So notice that how we are shifting, okay? So all of this shifting is happening in parallel at the same time. Okay. So it's very important to see this kind of shifting, how it is done in parallel at the same time if you are using a shift register. So the output of every flip-flop becomes the input, okay, at the rising edge of the clock, and all of them change simultaneously. All of them change simultaneously at the same edge of the clock. So remember that the flip-flop is sensitive to the edge of the clock, and all of these changes are happening at the same time. Okay, so it's very important to understand the timing of a shift register, and this timing can be shown in a table. So notice that, okay, if the next input here is 0, then notice that here we have, okay, 0, 1, 1, 0. So basically we are taking these actually 4 bits, and we are shifting them to the right, okay? Cycle by cycle, and you shift. So this is the timing of a shift register. It's really easy to understand. It's not really that difficult, okay? And remember that we are changing all of these flip-flops simultaneously, okay, at the same edge of the clock. So the clock is very important here because it synchronizes, okay, all the flip-flops which are used in this shift register, okay?
Doctor,
Q1
at the first cycle, how it is 1?
Well, that actually is stored inside it. So at T0, that actually is 1. So initially, I'm assuming that you have initially, okay, initialized, okay, Q3, Q2, Q1, and Q0. And then next cycle, you are shifting them. You provide a serial input here, and then you shift. Then you provide another serial input, and then you shift. Okay.
So like if we have if you asked us in the exam or in the
so
quiz,
if we reset, we start at 0, 0, 0, 0. If we reset. And then every cycle, you can provide one serial input and you start actually shifting it. Okay, in some cycles, it will be 1, sometimes it is 0. So eventually, you can have any pattern. You can store, okay, 1s and 0s inside these flip-flops and start actually shifting.
Okay, like it's given already.
Yeah, so then the input must be given to us. So yeah, so the serial input is given to us, and we are keeping track of the bits which are shifted inside these flip-flops.
Okay,
inside the shift register. Okay. Now, you can actually change the design. Rather than have serial output, you can have parallel output. So we still have here serial input, which is connected to T3. But notice that I have all of these outputs at the same time, Q3, Q2, Q1, and Q0. So we call this parallel out. So we have serial in, but parallel out. Okay, and we can read all of these flip-flops at the same time in parallel. Now, this is also another modification that we have done to the shift register to provide parallel output. This is very easy. We can just take the outputs of these flip-flops, and this is my parallel output. Now, this is actually useful in design. Yani these actually shift registers that we are studying in this presentation, they have some applications. And for example, suppose I would like to design an adder, okay, a bit serial adder. So this bit serial adder is not a combinational circuit, it is a sequential circuit. So for example, I would like to add A plus B, and let us say that A is equal to, let me give an example here. A is equal to 1, 0, 0, 1, and B is equal to 0, let us say here 0, 1, 1, okay? So I would like to add them. So when I would like to add them, rather than using a ripple carry adder, okay, which is a combinational circuit, I can use a sequential circuit like this one that will do the addition cycle by cycle, and this is called a bit serial adder, okay? So we start by adding, okay, this one plus this one, start at the least significant bits. So suppose that initially this flip-flop is initialized to 0, so we reset before we start the addition. So we provide here the inputs, okay, serially, 1 bit at a time, cycle by cycle. So initially this is 1 and this is 1. So the sum here equal to 0 and the carry out is equal to 1. So we get 1 at the output of this full adder. So this full adder is capable of adding only 3 bits, not more. But I would like to add n bits. So here I'm showing n equal to 4, but it could be any number of bits. So cycle by cycle. So now at the edge of the clock, notice that the clock is connected to this D flip-flop, and it is connected to this serial in parallel output. This is an n-bit shift register. So here we have n bits at its output. So suppose I would like to add n bits plus n bits. So the first bit that was actually computed is s equal to 0. So we shift in 0 here. That's my serial input. And we got a carry out, which is equal to 1. So after the rising edge of the clock, so this is the rising edge of the clock here, then this output is going to change from 0 to 1. And these inputs are going to change. This becomes 0. This is still 1. So what I really would like to do is I would like to add 0 plus 1 plus the carry, which is 1. I don't know if you can see it, but there is a carry. The carry out becomes the carry in, and we add it, okay? So we got here 1 plus 0 plus 1. We get another 0, and we get another carry out. So cycle by cycle, you can see that we are producing 1 bit at a time each cycle. And then after repeating n times over n clock cycles, then you get the final sum. So you are actually storing all of these bits inside this n-bit shift register. It is a register that can store the bits, and you are shifting them cycle by cycle. So you stop after n clock cycles, after you have done the addition, and then you are done. You can actually look at the sum. And for example, if you are doing the addition here, 1 0 0 1 plus you have this is A and this is B here, okay? Then you have actually here 0 0 1 1. So initially you start with the least significant, you get 0 and the carry. So the carry out becomes the carry in. Then next cycle use this full adder to add 1 plus 0 plus 1, you get 0, another carry. Then next cycle you get 1 plus 0 plus 0, you get 1, and there is no carry. So the next carry will be 0. Okay. And then you can actually continue like this. So here you get 0, 0 plus 1 plus 0 is equal to a 1. So basically you shift here 4 bits. So you start by shifting the 0, then the 0, then the 1, then the 1. So basically you get 0, then it was 0, and then 1, and then 1. And by shifting them to the right, after 4 cycles, you have the final sum. Okay. So you have to repeat this 4 cycles in order to get the final sum. You can also get the final C out, indicating whether there is an extra C out or not. Okay. So initially you reset, and then you start the addition bit by bit. So this is why it's called a bit serial adder. This is not really efficient. It is slow because you have to do the addition 1 bit at a time. I'm just showing to you how this addition can be done 1 bit at a time using a sequential circuit. We used here a shift register, and we used an extra flip-flop for the carry and a full adder, and that's it. This is all what we need to implement this bit serial adder. If you would like to implement this using a ripple carry adder, you have to use many full adders, and you have to propagate the carry. So today, designers, okay, don't use a bit serial adder inside CPU because it is slow. They will use a combinational circuit to do the addition, like we have studied before, okay? But I'm just showing to you how you can do it differently as a sequential circuit. Right. Let me show you another example. Remember when I talked about sequence detectors? Okay, we can also use a shift register, okay, to detect a specific sequence. So suppose I would like to design a sequence detector that is capable of detecting 2 sequences, 1 0 1 0 and 1 1 0 0. These 2 sequences. Now what I can do is that I can use a shift register. But now my shift register is shifting to the left, not shifting to the right. So this is my serial input. So we start by providing the 1, then the 0, then the 1, then the 0. So start at the most significant bit and then end at the least significant bit and shifting the bits to the left. After 4 cycles, you will get here 1 0 1 0. If you would like to detect the sequence here, what you need is just an AND gate. Now, to detect here a 1, all what you have to do is that connect a Q3. So this will be Q3 here. If you would like to detect 0, connect a Q2 prime. So this is a Q2 prime, because if this is 0, then this would be 1. Okay. Here, this is 1, connect here Q1. And this is 0, connect the Q0 prime. So when you end, okay, Q3 with a Q2 prime, with a Q1 with a Q0 prime, then the output will be equal to 1, indicating that we have detected the sequence 1 0 1 0. If you would like to detect a different sequence, all what you have to do is that change the inputs to this AND gate, and you can actually generate the output. Now, this actually sequence can be overlapping. It means that if we have, let us say 1 0 1 0 1 0. Okay. So you detect the first sequence here, and then you detect the second sequence here, and basically you get, okay, so basically you can actually get 2 1s here at the output after detecting the first sequence and after detecting the second sequence. So you can actually have them overlapping. But one thing you have to be careful about this is that here, okay, before you start, okay, the first step to do is to reset. So when you reset, you have 0 0 0 0. And my most significant bit that I would like to detect is a 1. So for this reason, okay, we reset before we detect the sequence, because you have to wait for 4 cycles until you see the first one, the most significant one. If you are detecting a sequence that starts with a 0 rather than starting with a 1, maybe you should not reset. You should reset the bits and wait until you get the most significant bit to be a 0. So you have to be very careful about this. So in this example, I'm detecting sequences here, okay, that start with a 1 here. Okay, you can see that here 1 is the most significant bit. So we have to wait until 1 appears at the Q3. So this is why we reset. We reset, it means that we clear all of these flip-flops initially before we detect any sequence, and we have to wait for 4 cycles, okay, until we detect this. Yani, for example, if you would like to detect the sequence 0000, then you cannot really reset. What you have to do is that you can set all of these bits to 1111 and then wait until the 0 becomes the most significant bit. So you have to be careful, as I said, about this. But you see that sequence detectors can be implemented with shift registers. And this is a different way of implementing a sequence detector rather than using a state diagram and writing equations. It's very easy, very simple. Okay. Questions about this? So this is another application of a shift register. Notice that here I'm shifting to the left. I did not really shift to the right. So I changed the direction of shifting. You can modify your shift register. Okay, you can actually have parallel in and serial out. So here it's actually is my parallel data input. This is my serial output. There is also a serial in, but there is a control. This control here is given by S, is just a single wire. You can actually change, okay, what this register does. And for example, if S is equal to 0, I would like to shift my data. If S is equal to 1, I would like to parallel load my N input bits. So you see that we change the functionality of the shift register according to S. So here, S here is used for selection or is used for control. Okay, so that's the importance of S. So you can actually make this shift register to work differently. You can make it to shift, or you can actually make it to load the data. And now, how do I implement something like this? Anyone would like to answer this question? How do I implement this this parallel in serial out shift register? Now notice that here I have a control, right? So this control input, you should not really, you should worry about this. You should actually think about this.
It will be the same. We will put multiplexers.
Exactly. We need actually multiplexers because we need actually to control these multiplexers, and the wiring will depend, of course, on the function that you would like to implement. So this is shown here in this slide. So I'm going to use multiplexers. Now notice that if S is equal to 1, notice that my parallel data input is it's I3, I2, I1, and I0. Notice that how they are connected to input 1. So if S is equal to 1, I'm going to select, okay, I3, I2, I1, and I0 and connect them. Okay, so basically the multiplexer, okay, is going to wire. Okay, so these inputs will be okay, fed to the inputs D3, D2, D1, and D0, and at the rising edge of the clock, okay, would change all the outputs at the same time. So this is a parallel load. We are loading the data. On the other hand, if I would like to shift, I'm going to use a serial input. Okay, for example, here I would like to shift to the right. So if S is equal to 0, not equal to 1, I'm going to select this input 0. So notice that this serial input is connected to D3. Now here D2, notice that how we are connecting Q3 to this 0 input. So therefore D2 becomes Q3, D1 becomes Q2, and D0 becomes Q1. So basically we are actually shifting, okay, to the right, and we have achieved here 2 functions. Okay, either we can shift or we can load the data, okay, according to S. So you can see that here we just use actually 2x1 multiplexers, and we can decide, okay, whether to shift or to load the data. Any questions about this? It's not really that hard, okay, to design these shift registers, depending, of course, on the function. Let me show you one more, which is called the universal shift register. Now, here I would like to have not just 1 bit for control, but 2 bits here for control. So S here consists of 2 bits. So we have 4 possible combinations. 0, 0, I don't really want to change the value of the output. Okay, so there is no change in value. 0, 1, I would like to shift to the right. 1, 0, I would like to shift to the left. 1, 1, I would like to do parallel load. So you can see that we can have multiple functions implemented in the same shift register, you can decide whether to shift to the right or shift to the left, or do not change the output, or even load the data into the register. So basically,
so
the shift
Doctor,
register, and then you can actually load the data into it. Yes, Usam.
So Doctor, we can use 4x1 multiplexers to implement each function.
Yes. So because we have here 2 selection bits, then I need actually here 4x1 multiplexers. So notice that I have here my parallel data input. This is if I would like to have parallel load. Here I have my right shift serial input if I would like to shift to the right. Here I have my left shift serial input. This is if I would like to shift to the left. So all of these actually are inputs, and the implementation is shown here in this slide. Yes, I need 4x1 multiplexers. Now notice that in the case of parallel load, let me start with S equal to 3. It's very simple. Connect I3, I2, I1, and I0. I'm showing it only for 4 bits, but really it does not really matter. Okay, if you would like to extend it to 8 bits, 16 bits, or whatever number of the bits. So notice that here, okay, we are using the input 3, okay, to load. So therefore, D3, D2, D1, and D0, they become I3. I'm going to select I3, I2, I1, and I0. And this way we can load, okay, this parallel input into the register. The register is implemented using just D flip-flops. If I would like to shift to the right, okay, let's say before that, let me say I would like to have no change. In the case of no change, all what you have to do is that connect the Q3 back to D3 using this input 0. Connect Q2 back to D2 using this input 0. Connect the Q1 back to D1 and connect the Q0 back to D0. So we can select, okay, the input 0 here to be Q3, Q2, Q1, Q0. And basically we are loading, sorry, we are actually just, so as if we are loading the same output. So this will not really change the output. So when you load the same output, it does not really change the output of the register. If you would like to shift to the right, well, you can use the right shift input here. This is my serial input. Notice that I'm connecting it to a 1, input 1, because 1 here means shift right. Notice that how we are connecting Q3 through this input 1 to D2. So this will become Q3, this will become here Q2, and this will become here Q1. Okay, so this is basically shifting to the right, and that's how we do it. Okay, you can reverse that, okay, using S equal to 2, and you can shift to the left, but you have to change the wiring. Okay, so this is here is okay, for this will be here input 2, that will be my left shift serial input, and you can track, okay, what are the inputs to the other flip-flops. So you can really design, okay, some complex shift registers this way. They are not really that complex, yani, but they have more functionality. Okay, and we have 4 different functions here, okay, in this shift register. It's called actually universal because it does actually 4 things. It can shift to the right, it can shift to the left. It might not really change. You can actually say that do not change its output or load, okay, the input into the register. Any questions about this?
Doctor, in all of the implementation we have seen, we are only using the D flip-flop. Why is that? Because it's just
because it's
simpler?
the most commonly used. It's the most commonly used. But when I talk about counters, you see the D flip-flop today is the most commonly used, and this is my focus. But later when I talk about counters, I'm going to show you another type of a flip-flop, which is the T flip-flop. So I'm going to show you how we can implement counters using the D type as well as the T type, because the T type can simplify the implementation of counters. So people have invented different types of flip-flops, but the one which is most commonly used is the D flip-flop, and this is why it is my focus. But I really would like you to understand the differences between these flip-flops. Okay, and we are going to encounter the T-type flip-flop in great detail, inshallah, on Sunday when I talk about counters in great detail. Okay.
So for registers, it is best to use D-type.
Yes.
Okay.
True.
Okay.
Right.
Thank you.
Because you just provide the data and you just actually store it inside the register, and that's it. Right. And shifting is very easy. You take the Q output and you connect it to the D input, and you can actually shift to the right or you can shift to the left, depending on the direction of the wiring.